get formers.
У меня спешат, я думаю, это правильно, может синхронизировать.
It's okay. Don't worry. Be happy.
Good morning, everyone. It's time to start our morning session, and the first speaker is Kashaev. He'll continue his lecture on Pachner moves and topological quantum field theory.
Thank you very much. Let us recall that what I did last time. So I introduced a certain object which is a linear map from a given vector space V, from the tensor square of a given vector space V to its tensor Q. And I imposed a trilinear homogeneous equation on this linear map, which graphically takes the following form. We put 6 vertical lines like this, and then, but first of all, we describe this Q in graphical form like this. And so here means the V tensor V, and here we have 3 copies of V.
And we map X from down to top.
From down to top, yes. So this is the action of the map. And then the equation can be drawn in the following way. So first of all, we put here, let me just to save some writing, put it just like this. And then what we have is this. Then we intersect here, then we continue like this. Then we intersect again, and we end up like this. And there are 3 open ends downstairs. And this should be equal if we again start with 6 vertical lines. And then before continue, we intersect 2 middle ones. And then we start from the right, like this. Then we intersect. Then we continue like this. We intersect again. And we finish like this. And now, on 2 sides of the equation, so the open end should be identified correspondingly. So this end, open end corresponds to this one, and so on. So this is the equality between 2 linear maps from the space. So equality in V tensor V tensor V to V tensor power 6. From bottom to top. Okay, so that's the equation, and then the question: what are the solutions? And actually, let me recall you that this is the image of a TQFT, and the image under a TQFT. Of a pentacoron, which means that so we have a U and the open ends correspond to boundary facets D0 of u, D2 of u, D4 of u, D1 of u, and D3 of u. Okay, so geometrically, so we should think of a four-dimensional simplex, and the identifications here correspond to corresponding gluings along the corresponding facets. Okay, so and this identity corresponds to Pachner move of type 3-3. 3-3. But there are two other types of type 5-1 and 4-2. Okay, now and I've given yesterday a class of solutions.
So the other two types, can they be written in the same terms?
Yes, yes. You should just do the following thing. For example, we can we can make undo this crossing and put it here, for example, and then we can in quotation marks invert this guy, which means that we put it like here, like this.
Yeah.
And erase it from here.
Yeah.
Okay, then we have two types. Now, this is a Q. This is Q, and this one, Q bar, which corresponds to opposite, or corresponds to pentagon with opposite orientation. Then it has three facets of opposite orientation and two facets of positive orientation, and so on. And this is a 4-2 move graphic. And you can go further, invert one more, put and arrive to 5-1. Okay, now today I am going to talk about only one class of solutions, which are very simple to define. And for the vector space, I am going to choose just Cn with its standard. Okay, I start with a root of unity, omega, a root of unity of order n. And then I take for b c to power n. And then now I will think of Q in terms of its matrix coefficients, I, J, K, L, M. So this is a EI standard basis. Standard basis. Let me put E bar with upper I. Dual basis. Basis of V dual. And then Qijk LM will be, we act by Q on EI tensor EL EM. So we get a vector in tensor cube of V, and then we apply to this a triple of dual basis vectors EI tensor E bar J tensor E bar K. So we get a complex number. And so I will write in a moment the explicit formula for this set of complex numbers, and namely for Qij Lm. And here I will think that Ij and so on M live in residues mod n. Okay, so integers considered modulo n. So these are group elements in the cyclic group. And then the formula is the following. So this is a normalization, 1 over square root of n, omega power ik, delta L, comma, I plus j, delta m, comma, j plus k. So that is a solution. Solution of Pachner 3-3.
And it is not of the type that you considered yesterday.
It is, if you erase this thing,
Yeah.
if you erase this, it is of the type I considered yesterday.
So this is like digraph Witten related somehow?
Yeah, but this is not high cocycle. This is just bicharacter. So you can take any locally compact group, abelian group, and put here a bicharacter, any bicharacter actually, even trivial one. If the trivial one, we will get the class of get into the class of solutions I described yesterday, co-commutative bialgebras. Here it corresponds to group algebra of the cyclic abelian group. But having this bicharacter is important for obtaining the complete symmetry properties of these weight functions. So far, everything is linearly ordered, and we distinguish between these 5 indices. And as you see explicitly, they do not enter symmetrically. And let me define the dual one, so which will be LMIJK, and so it will be just QIJKLM complex conjugate. Which means that we have to put minus right here. Okay, that's the definition of Q. And then the theorem. Okay, now I define the model. So let X be X triangulated four manifold. And then what I do is the following. So I define M omega applied to X is given by product over delta quorum W of P. Okay, sorry. Let me erase all this for manifold. First, I define a state. A state of X is a map F which goes from delta 3 of X to Z mod N. So delta I of X is a set of I simplices. Okay, so the state just a coloring of all tetrahedral cells by integers mod n, and then pentagonal weight W of P F is given by Q F of D0 of P, F D2 of P, F of D4 of P. So you understand the idea. So I'm putting just the same thing as I had geometrically, but now instead of indices I put the colors. D1 of P, F D3 of P. Is it visible from the back row? What I'm writing?
But if you erase the top of the vertical,
Yeah.
right.
Okay, let me try to make it in 2 colors. Yeah, let me rewrite. So P is a pentaquorum, or just the element of delta 4 of X, and then a W of PF is Q f of d0 of P, f of d2 of P, f of d4 of P, f of d1 of P, and f of d3 of P. Okay, if P is positive, positive means the following. So X is oriented for manifold, and then each cell, each four-dimensional cell gets a relative orientation because the linear order on the vertices induces the orientation of the cell, and you just compare if this orientation coincides with the ambient orientation of the manifold or not. If it coincides, we call it positive, and in this case we associate this weight function, and otherwise we associate Q bar with the same assignment. That's a temporal weight function, and then the partition function m omega of x is defined by product over all pentachora in the triangulation w of p f and summation over f. Okay, summation over all colors. And all this thing, sorry, I write m omega of x equal 1 over n to the power of number of vertices. That's a normalization. So that's the partition function. And the theorem tells the following. M omega of x is equal m omega of y if x is Pachner equivalent to y. Pachner equivalent.
Not only 3-3, but not only 3-3.
3-3, 4-2, 5-1. And independent. And this implies what I said, but I can add an independent of the linear order. So the orientations you can assign whatever you want. So it is complete invariant of the triangulated manifold in this sense. And then a few remarks.
So this is a theorem about this specific Q?
A specific Q,
or is it a theorem about every Q that solves your
no,
strange equation?
No. This is too much. No. Just Q, which is defined starting from a root of unity, omega. So this is why I indicate that we have a dependence on omega.
But and fixed orientation.
The orientation is fixed. The X is an oriented triangulation of oriented for manifold. And the remarks. So this is a unitary theory. So first of all, of course, easily extends to a TQFT. So if you have a triangulated for manifold with boundary, then you just fix the colors on the boundary and make the same summation over interior tetrahedra, and you get a vector.
Well, it's a sort of triangulated TQFT.
Triangulated TQFT, yeah, with corners even. But we ignore this this fact, just treat it as a usual TQFT. And the second is a unitary in the sense that m omega of x star, which star means opposite orientation, is m omega of x complete conjugate. And property under the connected sum multiplicative. which means that m omega of x connected sum y is equal m omega of x, m omega of y.
And which factor is added under disconnected sum?
Disconnected sum, yeah, it is also the same thing. Also the same thing. Okay, that's a theorem, and now let me just outline how the proof goes. So first, you check at least one instance. I mean, with a chosen linear order of each Pachner moves of each type. So 3-3 type is and all these verifications are easy. And in the case of 5-1 type, because our Q's are normalized, so the identity is satisfied up to normalization. Namely, for 5 Q's, 1, 2, 3, 4, 5, 2 will be always opposite orientation equals 1 Q, but with factor n. With factor n, and this factor n is the reason why the partition function is normalized by n 1 over n power of number of vertices, because the 5-1 type. In 5-1 type, so in this site there is a one interior vertex in the triangulated 4-ball, and so this removes one vertex, and this is reflected by appearance of the factor n. And this is why we normalize the partition function by 1 over n to the power number of vertices. Otherwise, all other relations just verified, and as you have seen, the weight functions are very simple, elementary functions, just a matter of direct, straightforward calculation that all Pachner moves are satisfied. Okay, and now about the independence of the linear order, and this is the most important part of the construction, and it is contained in the following lemma, which tells the following. So there exist two invertible maps S and T from V star to V, such that Q can be calculated. Now I think in terms of of Q in terms of as a vectors of the type V tensor V star V. Okay, it was initially it was a map from V tensor V to triple V. But as the vector space is finite dimensional, we can rethink of this linear map as a vector in that tensor product. And the order corresponds to boundary components D0, D1, D2, D3, D4. Okay, so this is why the conjugate space appears in the case of odd indices.
So in terms of the I, J, K, L, M of the before, it's I, L, J, M, K?
Exactly. So Q, I, J, K, L, M corresponds to Q, I, L, J, M, K. Corresponding to this order. Okay, then in this case, so the Q can be written as a permutation acting tensored with T bar, which is the inverse of T, tensor T applied to Q bar, which is the same as T tensored with P, tensored with S bar, tensored with S applied to Q bar, which is the same as S tensor S bar, tensor P, tensor T applied to Q bar, which is the same as T tensor T bar, tensor T, tensor P applied to Q bar. And this lemma is a key thing.
What are, can you remind what are P and T?
Yes. So P is a permutation. Right? Maybe I should put here P bar, P bar. So P is maps V star tensor V to V tensor V permutation. Which means that linear form phi tensor vector V is mapped to V tensor phi. A P bar is its inverse. P bar is the T inverse. And the same thing, T bar is the T inverse. This bar is S inverse. And for the moment, it doesn't matter the explicit form, what is the explicit form of S and T, but already this lemma implies the independence on the linear order. Because look what happens. So what does it mean, this P? So let me draw Q like this. So there's 5 open ends. And then the first equation tells us that this is equal to T bar, T.
But you didn't say what is T.
Yeah, I didn't say, so for the moment it is just an invertible map. Okay, for the moment. But I will show you the explicit form. It is also nice to see how it looks like. But for the moment, let us just accept that there is such T. And then graphically, this the first equation just means this identity. But look, what does it mean, the permutation here? Remember that the order of these open ends corresponds to the order of the face maps, right? Because they are linearly ordered. And then if we permute, that means that we exchange the first two vertices between themselves. And the result of this, and this exchange can be compensated by multiplication by some invertible operators along the 3 other legs. And now if you look at the second equation, then P acts on the second and third. So it is a permutation of the second and third. Then permutation of the third and fourth. And finally permutation of the last two. So these equalities describe us all the generators of the symmetry group acting by reorderings. And by composing them, we can generate any permutation we want. And the gluing rules of the TQFT are such that whenever you apply, you change some elementary order, then the corresponding multiplying operators will cancel out because this open end will be connected to some other open end, and as the gluing rules respect the order of the vertices of the corresponding tetrahedra, then the corresponding operators will match always. The one will be the inverse of another, and they will cancel. So this is the mechanism of restoring the symmetry. And as you see, it is not explicit, but it is implicit in the construction.
So there are 2 types of faces, therefore, the S type and the T type.
In reality, there are 3 types, but 2 types are transformed by one and the same metric in this example. And this type is given just by the following fact. So the tetrahedron has 4 faces, and then the type depends on which pair of vertices are exchanged. The first type, when you exchange the first 2 pairs. Second time, you exchange the second and third. And the third time, you exchange the last 2. So T corresponds to exchanging the first 2 or the last 2. And the S matrix corresponds to the exchanging of the middle 2 in the tetrahedron. Okay, and now let me just, to complete this picture, let me give you just the explicit form of these matrices, S and T, and you will see why the notation is such. S and T. and referring to Eric Rogel's talk of yesterday, so they correspond to his S and T. Okay, so what is S? S and T can be thought as elements of V tensor V, right? Because of duality. So initially it was a map V star was to V. Dually we can think of as the elements in here. So here is T. T is given by EI tensor E minus I, some function phi of I, sum of I. And S is given by EI tensor EJ, same function phi of I minus J, sum over IJ. And what is phi I? Phi I is such that if you take phi of I plus J, then it gives phi I times phi J times omega ij. And the second property of phi I is that its square is just omega I squared. So if you wish, phi I is just the square root of this thing. And but it has to be a function on the residues modulo n. So it is not straightforward. It is not enough just to put 1 over 2 to make. You have to make sure that it is n periodic. And the right definition of phi I is the following: I take any square root of omega and raise it to the power I times I plus n. And now look, if you take a square of that, you just remove this radical, and then this I doesn't matter because n is order of omega. So it becomes just omega to power I squared. But this definition is n periodic, because if you translate I by n, here it will be 2 times n. And this 2 eats up this square root, and n is a period, so this 2n disappears. But it reappears here, I plus n, and you get back to the same function. Okay, that's the definition, and then now you can see that on the so phi I is roughly the square root of this thing. So and then you can see that the T matrix in conformal field theory is given exactly by usually it's diagonal matrix, but here it is we have some little modification that it changes the sign of I. But structurally it is the same matrix as in conformal field theory. And another one, it's also the kind of S matrix. S matrix is roughly the Fourier transformation, and the same is here, up to modifications by similarity transformation. Okay, so that's basically the outline of the proof. And let me just, of course, the model is very simple, extremely simple, and it's hard to expect that the corresponding invariant will be very, very interesting. But nevertheless, it is not quite trivial. So first of all, let us make an example of calculation. Okay, S4. S4 is composed of P bar, two pentachora, which are put in the standard way. So you just embed one pentachoron in the S4, then the complementary part is another pentachoron with opposite orientation. So the partition function will be what in this case? It will be, so we divide by number of vertices, so the number of vertices is 5, right? So we put 1 over n to 5, and then we take two pentachoral weights, square root of n omega, q I j k lm times q bar, and we put the same indices because the corresponding faces are identified naturally, lm. and the sum over I, J, K, L, M. That's a partition function in the case of S4. And now you can see that this is one line calculation and 5. So 2 squares of n come out from the 2 q's. So we get one more n. And then the result, so the phase factors cancel out omega factors. So there remains only 2 pair of delta functions which are identical. So their squares coincide with themselves. So we get Li plus j delta m j plus k, sum over all 5, I, j, k, l, m. And these 2 delta functions remove 2 summations over L and over M. And what remains, we sum up once with respect to triple index. So it gives n to power 3. So we get n to 3 over n to 6 equal n over 3. That's a partition function of S4. And then now let me define m tilde omega, so-called renormalized partition function, which is given just by n to the power 3/2 of Euler characteristic of x times m omega of x. And then, since the Euler characteristic of S4 is 2, so 2 times 3/2 is 3. So n to power, if we multiply this thing by n to power 3, this becomes 1. So m tilde of S4 omega is 1. And now you can do similar calculations, and here I just list a few examples. M tilde omega of x, and here I put x. So S4, as I said, is 1. S3 times S1 is 1. S2 times S2 is 3 plus minus 1 power n over 2. S2 times S1 times S1, same thing. Let me call this epsilon n. Epsilon n. And then S1, 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 epsilon n to power 4. And the final thing, CP2. CP2, 1 over square root of n, sum over k from 0 to n minus 1, omega k squared. Okay, so I think I stop here.
Can you write some length space multiplied by
length space, L31 cross S1 is 1.
In the theory of derived Wiener invariants, there are so-called ideal derived Wiener invariants, when instead of taking some concrete complex numbers, you take some ideals in some polynomial rings, and it was done by Zimon-King. So I think it should work here.
Yeah, I think also. Yeah. So the only thing we have to care about is this root of unity omega, but it can make sense in any ring actually. So yeah, that's a good point because of multiplicativity property, this invariant doesn't detect any smooth structures. But if, for example, the invariant of S2 cross S2 would be some kind of nilpotent element, which is possible in some ring, then this would be a good point from the possibility of detecting smooth structures, because if we take connected sum with sufficiently many S2 cross S2s, then the invariant will stabilize due to nilpotency of the invariant.
But what about smooth structure? It will
Sorry?
stabilize?
No, here it will not stabilize. This is multiplicative. So you just keep multiplying by it.
So this looks an awful lot like that. is this model of Kashaev homological?
You mean in integrable systems?
Yeah.
Well, no, Fatiev homology is more complicated, I should say. This is just Fourier exponent, the only thing.
Yes.
It's much simpler.
More questions? If not, let's thank the speaker again. And we resume at 11 o'clock, in 20 minutes.
You can simplify this one.
Yeah, I know, but it's actually value is not, this I know. So, but sometimes it's zero, right? It can be zero minus one.
Yes, so I have to present
Yeah.
So there's a counts.
But the figure is not well defined. It's eighth of unit.
Не, они не разные.